Hello and welcome to this video on transfer functions in control systems. We're going to take a brief overview of what we mean by a transfer function and also apply this to some examples of equations of systems that we've derived in previous videos as well. So to help explain what we mean by a transfer function, let's jump straight into our first example here, which is an RC circuit, where we see that the output of our circuit is the voltage that is measured across the capacitor. In a previous video, we derived this equation for this system. And if you're not sure about where this equation's come from, I suggest watching our videos where we derive these sorts of equations for a range of first and second order systems. Anyway, we have this equation and you'll notice that it's in the time domain. Our voltages, the supply voltage Vs, and the output voltage across the capacitor, Vc, they're both functions of time t. Now previously we've defined the gain of a system as being simply the output over the input. And so in our case, the gain would be Vc of t over Vs of t. But looking at our equation, we'll quickly see that this is going to be very difficult to accomplish. It's a first order differential equation, and we see that we have Vc here and its derivative here too. Rearranging this into the form of Vc over Vs is going to be a bit of a challenge. And so this is where Laplace transforms come in. Rather than referring to the gain, we're going to refer to the transfer function. And the transfer function is defined as the Laplace transform of the output over the Laplace transform of the input. The transfer function itself we've given as a capital G, and it's a function of S because it's now in the S domain after we've performed the Laplace transform. If you're unsure what I'm talking about with Laplace transforms and S domains and that kind of thing, I'd suggest going back and reviewing our videos which introduce the topic of Laplace transforms and inverse Laplace transforms with lots of examples, because we're going to need both in this topic. For this video though, I'm going to assume that you're familiar with Laplace transforms and we're going to jump straight in. To start with, let's revisit our table of Laplace transforms. And again, if you've watched our previous videos on Laplace transforms, you'll have seen this table before. Before we begin with this table, notice that some of the entries are marked in red, and these represent initial conditions in a system. And the reason they've been marked in red is that in most cases, certainly in our examples, we can actually ignore these terms if there are no initial conditions in the system, or if these initial conditions are equal to 0. What do I mean by this? Well, in our series RC circuit, for example, an initial condition might be if the capacitor was already holding some charge, or if some current was already flowing in the circuit before the input is applied. In a mechanical system, an initial condition might be that the system's already in motion before the input is applied, that kind of thing. So these situations are possible, but in our examples, we're going to assume that we have no initial conditions or that they're equal to 0. And that helps to simplify things because these terms are going to disappear, which we'll see later on as well. So let's get back to example 1. And we had this equation here, RC multiplied by the derivative of Vc with respect to time plus Vc with respect to time is equal to the supply voltage with respect to time. And if we use our table of Laplace transforms to transform the left and the right hand side of our equation, we'll see something like this. So in case this is unclear, our differential here, Vc with respect to t, is similar to d of f with respect to t in the Laplace table here. And we see that this transforms to s f of s, assuming no initial conditions. We've ignored these red terms here. Notice as well that in the S domain, we typically use capital letters for functions, whereas in the time domain, we're using small letters for functions, and that just helps to mark the difference between the time domain and the S domain as well there. A function of Vc of t, this this second term in our equation here, is simply a function of time, and that corresponds with f of t in our table. You might even miss this, it's in the header row of the table here. And so that's just a function of time, and so it transforms to a capital F function of s in the S domain there. You'll notice also that in the S domain I've referred to this output voltage as VO, O for output, rather than VC. It doesn't really matter, you could call it VC, but you notice I'm using that capital letter there for the voltage, but I'm just using O here for the output. And similarly on the right hand side we've got another function of time, Vs of t, in the S domain. That's going to be V, what I'll call Vi of S, the input voltage, now in the S domain, using a capital letter as well there. So part of the reason I've referred to these voltages in the S domain as VO output and VI input is just to remind us, help remind us when we're rearranging, we want in the form output over input in the S domain to find the transfer function like we defined at the beginning. But before we do that, let's just tidy this equation up a little bit, because we can factorize just a tiny bit. We can draw out a common factor of VO of S, and that factorizes to something that looks like this. We've got VO of S multiplied by, in brackets, RCS plus 1, and that's equal to that input voltage VI of S. So now we've performed the Laplace transform of both sides of our function, and earlier we defined the transfer function as this here, the Laplace transform of the output over the Laplace transform of the input. Well, the Laplace transform of the output is VO of S, and the Laplace transform of the input we've called VI of S. And so simply we're going to rearrange our function into this form here. So to do that, let's first divide both sides by VI of S, and we'll have something that looks like this. And then we'll divide both sides by this bracket here, RCS plus 1, and we end up with something that looks like this. So you'll notice on the left hand side here we have VO of S over VI of S. That's our transfer function, which we could also call G of S. And so our transfer function in this case is equal to 1 over RCS plus 1. Now, in this video, all we're doing is we're going to derive some more transfer functions like this. We're going to use transfer functions in later videos and get into more their application. But in this video, we're going to look at some more examples along the same lines. We're going to derive some more transfer functions like this. So our second example of a system or circuit is this RL circuit. So very similar to the first example, except rather than an RC circuit, it's now an RL circuit. And again, we have our supply voltage here, and the output voltage is measured now across the resistor. And we previously again derived this equation in another video, which you may want to revisit, but this is the equation that we derived for this circuit. We've got L over R multiplied by the derivative of VR with respect to t plus VR of t is equal to Vs of t. Let's apply the same principle to find the Laplace transform of this equation. Again, we're assuming that the initial conditions are 0 here, and we find something that looks like this. So notice a few things. I'll not sort of repeat myself with regard to the Laplace transform here, but notice that we have this constant of L over R, and we can keep that outside of the Laplace transform in this case because these are constants. L and R are constants, and so we have something like this, and we can simplify a tiny little bit. We can take that S and make it part of that fraction as well, and so we have something along these lines. And just like our previous example, the output function that was the voltage across the resistor in this example is now what we call VO of S, and the input function, which was the supply voltage, Vs of t, is now given as Vi of S. And again, we can factorize this a little bit. We can take VO out as a factor here, and we get something like this. We have VO of S multiplied by, in brackets, SL over R plus 1 being equal to VI of S. And so again, the transfer function is simply a case of rearranging this into the form of VO over VI, output over input. And in this case, we can divide both sides by VI. We get something that looks like this. And then divide both sides by that bracket, and we get something that looks like this. And so our transfer function in this case is expressed by this 1 over SL over R plus 1. Now, the way that this fraction is presented here, we've got these sort of nested fractions here. There's a fraction in the denominator of the fraction, which I don't really like so much. So we can multiply all the terms on the right-hand side by R to get rid of that fraction. And we'll end up with something that looks like that, which is a bit tidier. This wasn't incorrect, but it's just a little bit more simplified in this form here as well. So we've got now our transfer function G of S being equal to R over SL plus R. Here's a third example, and in this particular example, this is a mechanical example, whereas the previous examples were electrical circuits. Here is a MASH dashpot system, and it's another example of a first order differential equation where we took the input as the force applied to the system, F of t, and the output being the force on the dashpot, F d of t. And so we have this equation here. Again, we derived this in a previous video, but using the Laplace transform table, and again, assuming no initial conditions, we get something like this in the S domain. I'm just conscious of the fact that I'm jumping through several steps here in terms of Laplace transforms. Again, I'm assuming that you're familiar. I'm not using the Laplace notation and that kind of thing. For more sort of step-by-step examples of Laplace transforms, I recommend going back to those videos where we introduce the Laplace transform and the examples are worked through a bit more sort of step-by-step. But here I'm sort of jumping straight from the time domain to the final result in the S domain here. So I'm hoping you're following along there. But in this particular example here, you'll notice that the output we said was the force on the dashpot. It's now called FO, the output of the system, and the force applied, which we called F of t, is now Fi in the S domain, the input force here. And again, we can simplify this slightly. I'll just take that S and make it part of this fraction here, and that's going to help us to factorize in a similar manner. We're going to take FO, the output force. We're going to take that out as a common factor and leave this bracket 1 plus Sm over mu, and that's equal to the input. Rearranging again into the form of output over input, we get something that looks like this: 1 over 1 plus Sm over mu. And again, we've got this kind of fraction in a fraction, which I don't particularly like. We can multiply all the terms by mu in this formula here to get something that looks like this. Just two more examples here, but these are going to be examples of second order systems. And so the fourth example here revisits one of the previous equations that we derived in our section of second order systems. And this is for a series RLC circuit, and the output of this particular model here was taken to be the voltage across the capacitor VC, and we've again got our input being the supply voltage VS, and we derived this formula here. Again, it's a second order differential equation. We've got RC multiplied by the derivative of VC with respect to time, plus LC multiplied by the second derivative of VC with respect to time, plus VC of t is equal to that input Vs of t. And again, we're going to refer to our table and we see that we can take these constants here, RC, LC. These are constants. These don't fall under the Laplace transform, but any function of time is going to be affected by the Laplace transform, and we get something that looks like this. We've got RC multiplied by S, VO of S, plus LC, S squared, VO of S, plus VO of S is equal to VI of S. So notice again, I'm using this output and input notation here. Let's just have a quick glance at the Laplace transform table here. So you can see here that our first derivative corresponds with this entry on the table. And so we have S, VO of S. We're again ignoring these initial conditions. The second derivative, again, we've got initial conditions that we can ignore. And so we end up with S squared, in our case, VO of S. And just an ordinary function of time, Vc of t, is going to become VO of S in our case here. And same for this Vs of t, it's going to become Vi of S. And so again, notice that we've ignored the initial conditions in this particular example, which fortunately for us keeps things nice and simple. Again, notice that these constants RC and LC, they just remain the same. They're not affected by the Laplace transform here. We're going to factorize this expression here that we've got here, because VO of S appears in each term on the left hand side. We can take that out as a common factor, and so we end up with something that looks like this. We've got VO of S multiplied by in brackets SRC plus S squared LC plus 1, and that's equal still to this input voltage in the S domain, Vi of S. And so finally, the transfer function, same as our previous examples, VO of S over Vi of S. Well, we can rearrange this equation here and we get something that looks like this. We get 1 over SRC plus S squared LC plus 1. That's all on the denominator there. The last example for this video, it's another second order system, and it was a mechanical system involving a dashpot, a spring and a mass. And again, it's a previous equation that we derived in another video, and it looks like this. We've got Fs of t mu over k multiplied by the differential of Fs with respect to t plus m over k, second differential of Fs with respect to t, and that's equal to the force applied Ft. And so the output in this case of this particular system is the force on the spring Fs, the force on the spring there, and we have the force applied to the whole system F of t on the right hand side. And so again, very similar to our previous example, these mu, k, m terms, these are constants. They're not affected by the Laplace transform. We can apply the Laplace transform to just those functions of t. And very similar to our previous example, the RLC circuit, we're going to see something that looks like this. We've got FO of S. Remember that force on the spring is the output force, so that's F of O of S in the S domain, plus mu over k S FO of S plus m over k S squared FO of S is equal to Fi, that input force, Fi of S on the right hand side there. Again, in a very similar way, we can factorize. We can take that FO of S out as a common factor, and we get something that looks like this. FO of S, all in brackets 1 plus S mu over k plus S squared m over k, and that's equal to Fi of S still. Rearranging this a little bit into the form of our transfer function, we get something that looks like this. Again, we've got these sort of fractions within a fraction in the denominator here, And so we can solve this problem. You see how they're both divided by k. We can just divide everything, top and bottom, in this equation by k. And if we multiply everything by k in this case, we're going to get something that looks like this. K over k plus s mu plus s squared m. And that's our transfer function for this system. So in some of our following videos, we're going to actually see how we can use these transfer functions, but hopefully this video has been useful to see how we can derive them using the Laplace transform.